Welcome everyone to this episode of Policy at McCombs with the Salem Center for Policy at the UT Austin. I am very pleased to have with me Dr. Ed Calabrese, Professor of Toxicology at UMass Amherst. Ed is the author of more than 1,000 peer-reviewed journal articles and the author of more than 10 books. Ed has dedicated the last 20 years or so of his career to understand the nature of the dose response. And today's talk, we're gonna shed light on what is a dose response, why is it of relevance to policy, to any layman, and how it affects our most intimate of policies, from health to our energy policies. Without further ado, welcome, Ed.
Thanks very much, Dima. I'm happy to be here.
Well, Ed, without taking too long, I'm going to dive right into it, and I'm going to ask you, what's a dose response?
A dose response is basically something that everybody is pretty much aware of. It's a relationship between an exposure and an outcome, and that means it could mean, for example, how much you eat versus how full you feel. I mean, there's a relationship between the two. Or if you're having a glass of wine, it could mean how much wine you drink before you feel a little bit lightheaded, or it could get a little bit more complicated. It could depend not really how much wine you're drinking, but how quickly you're drinking the wine. In that case, it's probably a dose rate sort of a phenomenon, and the two kind of fit together. And it also relates back to things within the environment. For example, you hear exposures to many different types of things, such as lead in drinking water, perhaps, and there are dose response relationships. How much is safe? How much isn't safe? And it relates back to essentially a dose response relationship. Are there safe levels? Aren't there safe levels? Is every little bit always harmful? Is there a place that we can kind of feel safe? And this is what I think the public relates to. It even relates to exercise. A dose response for exercise. It can relate to how long you exercise is a dose response. How intense. It could mean how often. All these things get fit together into some sort of mathematics or metric, but most people just kind of have a gut feeling for what a dose response is. And I think in common terms, for example, at least for me anyways, I tend to resonate around something called the threshold, because I have a sense of, when something gets too hot, it crosses a certain line and it's too hot. So I kind of sense that there's a dose response for that, and for cold the same way, or for feeling uncomfortable. There's more or less, but yet, as simple as all these things are, and this is like our personal experience, this concept actually rules regulatory agencies like the EPA or OSHA or FDA. For them, it's not so simple. For them, they're worrying about actually what goes on at very low doses. How does everybody have the same dose response? Is what's safe for you safe for me? What happens for somebody like me who has all this gray hair? Did my susceptibility to toxins change because guess what? I got older. If when I was 23, would I have the same susceptibility if I have at my current age, or if you were 3 years old? And so it gets complicated for, we always see things within the context of ourselves. But regulatory agencies have to see the problem of dose response, within the framework of a society. And are they really trying to protect all 350 million of us? Can they do that? Who are these 350 million people? How many children are there? How many 1-year-olds? How many 95-year-olds? How many over 100 are they? Should they try to protect everybody? And how many should they protect? And how much is the investment? And protect them from what? For all kinds of effects. And so the dose response, and like everything else in life, how much you want to protect depends upon how much you value it. and how much you value it depends on, lots of things all fit together in some sort of a pattern.
So how does a scientist understand the functional relationship between, let's say, the dose of a particular substance and the response, whatever that health response or endpoint that we're focusing on? Do you look at clinical trials, epi data? Do you rely on theory? How does a scientist understand the functional relationship?
Well, I think scientists tend to look at what other scientists did. They look at their history. They look at what they were taught in class, and you kind of push it back. You push it back to what did the founders of pharmacology think, and what did the founders of toxicology think, and when did this dose response all start? Because intuitively we mentioned, most people probably think maybe there's such thing as a threshold that you have to exceed, but back in the day, you might say, when did it all start? When did people start thinking about dose response? Well, back in the day, it turns out to be for us about in the 1880s. And you probably, the audience may be aware of this thing called Listerine, this thing that people mouthwash. There was this doctor by the name of Joseph Lister who back around the Civil War time, he was over in England, but back around our Civil War time, he was creating a revolution in trying to have basically aseptic surgery. And surgery back before then was, and even after then, was really very contaminated with bacteria, very infectious oriented, not very good for the patient. And Lister made a big breakthrough. He found, he had been aware of some of Louis Pasteur's work. He was aware maybe that there's a relationship between microbes and the failures of his surgeries with all kinds of infections afterwards. And he first used a chemical to attempt to kill some of these microbes that might be causing disease and illness and injury in his surgical patients. And he had great success, although it wasn't meteoric. Like everything else, new idea, lots of people don't accept it, challenges. Eventually, the story is that he converts people over to his way of thinking, but the agent that he's working with isn't the best in the world. It has some imperfections, and so there's a need for better disinfectants, put it this way. And that's where the dose response really starts, because this German investigator by the name of Hugo Schultz back in the 1880s over in northern Germany, he decides to evaluate about a dozen agents, not on bacteria, but on brewer's yeast. And so he grows them, and he is really very enlightened study design, many doses, followed them over time, really pretty intriguing for an 1882 sort of a scientist. And so he expected all these toxic chemicals that he was testing, things like mercury and formaldehyde and other, kind of like the dirty dozen of the time. What he did was he gave a broad range of doses, and he expected them to just kill these brewer's yeast. And at high doses, they all did exactly what he was expecting and hoping to do. But he had a little surprise, and the surprise was that at low doses, they all were stimulated, and he couldn't figure it out. He'd never expected this. Kind of like that's what research is supposed to be about, kind of the unexpected and being wise enough to see the unexpected. And so he thought that he had screwed up, and either him or his technician, and they kind of did it over again, and they got the same result, and then did it over and over and over and over again, many times. They kept getting the same result. And so what happened is that threw their hands up in the air and they said, this must be real. And he went to his first ever presentation in 1884 at the Greifswald Medical Symposium in his little town, made his presentation. And that's where the story could have ended, but it really didn't end there. Because what happened to him, and this becomes crucial, an older faculty member heard what he had to say, and what happened at the same time was that Schultz had read what they call the homeopathic medical literature. And there was a paper that was published in that same year, 1884. And that paper was looking at a homeopathic remedy and was given to people with gastroenteritis. And it seemed to cure all these patients. And so Schultz was interested in, and it was, and right at that same time, in the famous laboratory of Robert Koch, a little bit down the road. They had just discovered the bacterial cause of gastroenteritis. So Schulze went over there, got essentially culture, came back to where he was, and then he tried to see if this homeopathic drug would actually kill the causative agent of the disease they're claiming that the homeopaths claim to have cured. And when he checked it out in the lab, no matter how much of the stuff he put in his agar plate, they didn't kill anything. And so you might think that, well, he came to the conclusion that homeopathy, this drug that they were using, it didn't work at all, and it must have been something wrong with that study. But Schulze didn't think like that. And so he didn't know. But when he talked to this senior professor, they kind of put a theory together to answer every question. And the question, and it was really this, and this becomes very significant in our own lives today. And that is that they said, we think we know how the homeopathic drugs worked. They work not by killing the bug, the bacteria, whatever was the causative agent. We think it worked by enhancing the adaptive capacity of the body to fight off the infection. And they relied upon his study with the brewer's yeast as the backdrop for that. And so they somehow, I have to say, it was an element of creativity. The data really didn't support it necessarily, but that's how they integrated and put it together. Now, what happened next changed Schulze's life and ultimately changed my life, because what he ended up doing was, he claimed that he had derived the explanatory principle of homeopathy. And it was based upon an induction of an adaptive response, and that the dose response would be biphasic, a low dose stimulation and a high dose inhibition. Well,
and I believe you have a slide that you could share that would probably shed light on what this biphasic dose response looks like.
Yeah, I will. It's right here. And this little slide over here shows 3 different dose response models, okay? Now, back in the day when Schulze was, a young academic around 32, 33 years old, they didn't know anything really about dose responses. But Schulze comes out, and I'm showing a J-shaped response. I'd have to flip it on the other side for an inverted U. But what Schulze is showing is that he's getting some sort of a deviation at low dose, and then something opposite happening at high. And that's what the hormetic dose response is. I'm showing you a J-shaped dose response.
Okay, so just to understand, below the dotted line, that is a positive health effect. That means it's not adverse. Only above the dotted line, that is an adverse health effect, correct?
The way we're interpreting is this would be a situation where the yeast are doing better. They're surviving, they're metabolizing more. Above that line, they're actually doing progressively worse. And in this particular case, you could look at it from a different perspective. You could say this could be also looked at as perhaps heart disease or a stroke or some cancer or mutation. That this J-shaped response shows a decrease at low doses and an increase at high. But in fact, there are 2 other very prominent models that we have today that really rule the roost in terms of modern toxicology, modern risk assessment, regulatory activities. And these are listed on the slide. And this is what I grew up with. I grew up with this threshold model and this linear model. And I've talked a little bit about what the threshold is. Threshold is, oh, gee, you have to go up to a certain level. Nothing's really happening much. And then you go past that level and there's a deflection, there's an effect. It's kind of like I could have, a half a glass of wine and not feel lightheaded. Then I kind of go past that half a glass of wine and I'm starting to feel lightheaded. I passed the threshold. Now, the linear model would be quite different than that. The linear model would say, gee, if I kind of just take a little sniff of that wine, I'm going to start to feel lightheaded, and it's going to get progressively worse all the way up. So there's almost starting at essentially the first molecule that you will actually experience. Whereas the hormetic, this biphasic sort of a model that you see here, and I'll come up with, tell you a little bit later where that model name comes from and so forth. But that's what Schultz was talking about. But Schultz back in the day, he didn't know the name we call it today. We call it a hormetic dose response because some university professor at the University of Idaho back in 1943 saw this with fungi and named it hormesis, from the Greek meaning to excite. But Schultz back in the day, they named things after themselves, you know. So he named it after him and his professor friend. So they called it the Arndt-Schultz law for this J-shaped sort of a dose response. But it lost favor, so to speak. But in certain parts of Germany today, they still call it the Arndt-Schultz law, especially in northern Germany. It's very weird, but maybe they'll come around after a while. Maybe they won't. But
and I would like to point out that your research on hormesis, or this J-shaped hormetic model, is what inspired Nassim Taleb to come up and coin with the term anti-fragile, which is now widely used, but very few people know that actually the core of that word is your research on hormesis, that there are certain systems that get stronger when you shake them or when you stress them at low doses, obviously.
Oh, that's right. That's right. And all roads lead to hormesis, more or less, however you want to call it. So I'll drop the share screen here and go back here. Yeah, but what happened to Schultz is it's an interesting story, because Schultz was a young guy, young professor in a traditional medical school. And back in the day, in the 1880s, there was a profound conflict between homeopathy and traditional medicine. And I mean profound. It's like they're at each other's throats. Now, we wouldn't think that's the case today because homeopathy is so diminished and modern medicine is so strong. It's like, you know, a midget against the giant. I mean, you just wouldn't, but back in the day, they were kind of equal. And Schultz made the problem that he was a traditional medical school professor. And guess what he did? He sided with the enemy, and the enemy was homeopathy. And very right off the bat, Schultz, he learned something about human nature. They weren't so open-minded back in the day. Maybe they're not so open-minded today about, you know, different ideas. Well, I can tell you, Schultz paid a significant price. He and his idea of a biphasic dose response became marginalized pretty darn fast. And if you were a good professor at the University of Greifswald back in the 1880s, you made your way to the real powers of academic leadership in Germany. You know, Leipzig, you went to Berlin, you went to, you know, other places. You didn't stay at Greifswald. He stayed at Greifswald until he died in 1932. And so what happened was that he tried to make inroads, but he really couldn't, and he wasn't a fighter, and he was ridiculed. And what happened was that modern medicine really begins to flex its muscle with a lot of leadership in the UK in the early part of the 20th century. And they have some really brilliant neuroscientists, pharmacologists in England. And what happened is that a couple of them really took aim on Schultz and took aim on his idea, and they decided to crush it. And at the same time, pharmacology has to have a dose response, and so they're beginning to do lab work and lots of other things. And what they do is they sure as heck cannot accept this biphasic dose response of Schultz, because that's the dose response of the enemy. So they all gravitated over time to adopt a threshold model that resonated with their laboratory work, it resonated with their common sense and their personal experience. And the next thing you know, articles and books were being written pretty much linking and associating Schultz with medical quackery, homeopathy with medical quackery. Schultz really wasn't a combative guy. He was also getting old. He had a couple of sons who died from, I think it was diphtheria. He had a very complicating life, even though he was, I think, a very smart and gifted man. But and as talented and as great as these British pharmacologists and some toxicologists were, some of the leaders actually were totally dishonest in how they characterized what he said, what he did, his work, and so forth. I've gone into the historical literature, and not really to be Schultz's, big defender, but really to set the record straight, where they really unfairly represented what he said and how he said it and so forth. And just to put this in perspective, in this country, in the year 1900, so 120 years ago, there were 23 schools of colleges of homeopathy in this country. By the time it was 1923, the year Schultz had retired, there were 3. So homeopathy was going down fast. Schultz reached 70 years old in 1923, and homeopathy was basically hanging on for dear life and pretty much dead. And traditional medicine was on this meteoric rise that we know where it is today. And they were taking this magic carpet ride, really basing their work and basing how to study things on this threshold dose-response relationship. Everything was based on a threshold. No real biological activity until you got up to a threshold, and then bingo, you have a threshold. And then something really weird happened. There was another phenomenon that was taking place. And that phenomenon was in the world of radiation biology, radiation genetics. And it was hard to really predict what was going to actually happen here. But unrelated to the dose response, at Columbia University in the United States, there was what they called a fruit fly lab under this guy, Thomas Hunt Morgan, who would win a Nobel Prize in biology and medicine in 1933. But they were really trying to study mutations, and they were trying to understand what caused mutations. And there was a big race that was developing, and the race was to try to figure out what the underlying mechanism of biological evolution was. Now, we all know the origin of species by Darwin, and then there was Gregor Mendel dealing with the segregation of genes in sexual reproduction that followed. But there was no underlying mechanism of evolution, except it really had to be related to mutation. But just how did nature induce mutation that would ultimately become selected for and become part of an evolutionary process? And so Thomas Hunt Morgan and his band of young graduate students, a number of them are pretty brilliant young graduate students, they went after it in a big way using the fruit fly. And they knew that they had seen through casual observations of fruit fly. In fact, the first time for Morgan, he had a technician in his lab, and the technician pointed out to him on the floor there was a fruit fly with a white eye. And these fruit flies had red eyes. And Morgan knew that he was on to something. And that was kind of like this seminal little observation that made him really focus on Drosophila and try to find ways to induce this, because that seemed to have happened like a natural mutation kind of a thing. So what happened is that these eager beaver young graduate students, they took every noxious chemical you could find. They took X-rays, they took radium, they took whatever they could do to throw at this little fruit fly. And they took, excessive heat, excessive cold, mixtures of things. They shook up everything. And guess what? You would think it'd have been the easiest thing in the world to induce mutation in this little dinky fruit fly. People do it all the time. You can induce these mutations in a high school class, for that matter, right? These were very smart people, okay, and they could not do it. They could not do it. And so what happened is it's like 1910, 1912, and then we're gonna, a number of people got their PhDs, but they couldn't get them on that issue. And so, but one of those people who got a PhD in that group, guess what? He migrated to, he migrated to Texas, and he became a professor at the University of Texas at Austin.
What a coincidence.
Yes. And his name is Herman Muller. And so Muller was a very unusually gifted person, talented in many different ways, and a very hardworking man. And he was one of these these hardworking grad students that just kept trying. he just kept trying. He wouldn't stop trying. I mean, we're talking 17 years trying, right? But
And
he's
trying to induce mutation in fruit flies to try to answer Darwin's original question.
Exactly.
Right.
That is the question. How does this relate back to modern medicine? Because we were talking about Schultz and thresholds and these British pharmacologists and all that sort of thing. And there's Mueller just working on fruit flies in a little lab over in Austin, right? And so what happened is that he made certain developments, certain structural changes in some aspects of his fruit fly that made them able to be a bit more sensitive and give clearer results. And as it turns out, in November of 1926, in his lab in Austin, Herman Muller, he observes for the first time a somewhat rapid occurrence of fruit fly offspring that are mutated. And he is extremely excited. This is actually a pretty major breakthrough. And so as it turns out, he would continue this. Well, he does 3 experiments while he's there in this. And these are 3 experiments which will ultimately lead to him winning the Nobel Prize in 1946, because he becomes the first to actually induce gene mutation.
So when he won the Nobel Prize, was he at UT Austin, or he won it for the work that he did at UT Austin?
He was not at UT Austin. He left Texas around 1932. He left in sort of a bad way. Wasn't really happy with his life at the time. Some of it was due to his relationship to the school. Others were just due to the greater complexities of life. And he had a rather vagabond sort of a life. He went to Germany on a Fulbright. As soon as he got over in Germany, it was 1933, and the Nazis had taken over. He got kind of arrested for a while, then they let him go. And then he was very sympathetic to the Soviet Union, and he left Germany and he went to the Soviet Union, and they knew he was a prominent man. They gave him a great lab and moved him from around to where he needed to have all the pieces in place to be good. But he's very outspoken, and he could tell anybody off, and so he basically offended Stalin, and he had to get out of the Soviet Union fairly quick as well. And ultimately he makes it over to Spain, and he fights in the Spanish Civil War, riding an ambulance around, and makes it over to the University of Edinburgh. And the Rockefeller Foundation actually picked up his salary while he's there. And Mueller is, Mueller's still, he's on this journey, but I can tell you for sure that even though Mueller in 1927 will claim that he induced gene mutation, it wasn't that everybody believed in his results, all these. He was, in science, you have to fight and prove and reprove and all this sort of thing. And so while he was at Edinburgh, he got a grad student to do a PhD under him, which he felt supported some of his interpretations. And then bingo, World War II was happening, 1938-39 over in Europe, and he has to get back to the States. And so, but because Mueller is cantankerous, he's impossible to get along with. He's very good. He's very good. Okay, he's very talented, but he's complicated. He's a complicated person, and so.
And Mueller, to my understanding, is the person who gave rise to this alternative model to the threshold, which was the dominant model at the time. And that model is the linear non-threshold. Am I correct?
Yeah, and I'm going to swing back. I'm swinging back to that, but I'll get him back to the U.S. So he comes back to the U.S. in 1940, and believe it or not, he ends up in the town that I'm speaking from right now, Amherst, Massachusetts. I'm at UMass, but he's over at Amherst College, and then he's there for 5 years, the duration of the war, because during the war, the U.S. was basically drafting all these Amherst College professors. They needed to backfill with somebody, and Mueller became one of the people that they hired to fill in. And he got hired actually because one of his old grad student buddies, Harold Plow at Columbia, remembered him well. And so that's why Amherst hired him, was because his old graduate student friend from Columbia, greased the skid so he could come in here. But as it turns out, Amherst Amherst is like a #1 undergraduate ranked by U.S. News and World Report, right? And so they, just to show how brilliant they were, after 5 years, they decided not to renew his contract. So he goes to Indiana and he gets awarded the Nobel Prize the next year, in some brilliant sort of irony. And so, so as it turns out, this is the full cycle of Mueller. But we'll go back to Mueller of 1927. Mueller he really wants this to happen. He's trying to, he knows that if he can induce gene mutation, that he's going to get the big prize. And the big prize is probably going to be the Nobel Prize. It's a big deal. And so he sees in his first experiment that he has actually done, and back in Austin, that he's induced what he believes are radiation-induced gene mutations in these fruit flies. And so what happens is that he begins a second experiment in the spring, and then he has a third experiment in the summer of 1927. But something unusually happens in this case. Other people, Muller's not the only one who's going for the prize. There are other people that are competing with him, and there are botanists, and there are others that are going for it. And then in January of 27, there are two people from New York City area. They publish a paper in the Proceedings of the National Academy of Sciences, and they're claiming to have induced gene mutation. A very, very limited case, but they claim to do it. And the Proceedings of the NAS is a big time journal. It's not like, it's a backwater journal. And back in those days, it was even bigger in terms of its significance, right? And then, but he's being chased by others that are maybe ahead of him, maybe behind him. He doesn't know. And so, but he knows one thing: he wants to be first. Okay. So how do you get first? He's got one experiment. Maybe it shows something, maybe he doesn't. He knows he has other stuff to do, right? So, but what Mueller does, he's in the midst of a second experiment, which seems to be confirming his first. He gets, to the surprise of everyone, he gets a paper published in the journal Science. Gets published in I think it was July 22nd of 1927. And it was called The Artificial Transmutation of the Gene by Herman Muller. And Muller is claiming that he has induced gene mutation, and that he introduces a term called point mutation, which is very tiny mutation. They didn't know about nucleotides in the structure of genes and all that back in the day. So it calls it a point mutation. It's a mutation within the tiny, 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 tiny gene. And now other people had seen genetic changes by having big chromosome changes, and the chromosomes could refuse together, and they could see changes in the next generation of fruit flies, things of that nature. Muller discounted that as having no significance at all, really. Muller's really trying to understand genetic changes, mutational changes that would be relevant to evolution. He thinks they're going to be micro changes, and his gene mutation. And so this becomes his main focus. But the interesting thing, if you tend to have an interest in the history of science, and I do, I wanted to go back and read that Mueller paper, that 1927 paper in the journal Science. So I remember one day going back and getting that paper and getting a copy of it and attempting to read it. And then I was really surprised. There wasn't any data in the paper. It was Mueller talking about some experiments that he did, but he never showed any data. But yes, this was like the most significant discovery. This could lead to a Nobel Prize. I mean, you got to show you proof, right? And so, and I kind of reflecting on myself. I mean, by that time in my career, I was probably over about 30 in my submissions to science. And when I submit a paper to Science, there's a lot of data. And still, I'm every time you're lucky to get a review. It doesn't really happen too often. It has to be something special. But I said, Mueller, what could have been so special that Mueller and science would have published his paper announcing this big discovery without actually having the data there? That's bothered me a long time. And so I've spent some time trying to figure that out. Well, as it turns out, the Journal of Science, which is the official organ of the AAAS, the Association for the Advancement of American Science, it's a big time operation, major. Well, back in 1927, it was the official journal of the society, but it was not owned by the society. It was privately owned. And it was owned by a man who had been a professor of psychology at Columbia University, who bought it in 1893. And he kind of helped restore it and brought it to some prominence. And this gentleman became a very close friend of Thomas Hunt Morgan, who was Mueller's advisor. So Mueller's advisor and the editor of Science were kind of like close. I mean, you know, not quite like two peas in a pod, but very, very friendly, professionally and personally friendly. And Mueller published a few papers there. So Mueller, I don't know how he got it into the journal. I've really looked. I've gone into all Mueller's papers and this gentleman's papers. I've gone and tried to get all this information out of Science. I don't know how it worked out, but I know that
so according to you, there is evidence that the scientific process was not followed properly, to say the least, when it comes to the publication of Mueller's paper.
Well, in two different ways. One, on behalf of Mueller, trying to not play by the rules, and where you had multiple people, and I know of multiple people who were really breathing down his neck who played by the rules, and that means they go through peer review, and they have to take their lumps in peer review and go back and maybe do more experiments and do other things. Mueller wanted primacy. He wanted to be first. And this guy, Cottrell, Dr. Cottrell, he basically got, he gave him, you know, that you might say prize. And so what happened was that Mueller still, when Mueller was, I believe, had to be submitting his paper into Science, is probably the middle or end of May, given just the procedures for getting things printed and everything else. I know for sure that Mueller had not finished his second experiment. I know for sure. I have purchased the entire, you know, Nobel Prize notebook, and I could track the language in the paper in Science with what was going on in each experiment. And from first to second experiment, there was a change in model and a lot of other changes. And he didn't get into that in the Science paper. So I knew that Mueller only was talking about his first experiment.
And this scientific mishap had huge consequences in the world of dose response, which we still feel up until today. Is that correct?
Well, yeah, I'll get into that right now. But what I'll tell you is that even though Mueller got primacy because he made it in the big journal with his, you know, name on this paper with no data, everybody was waiting to see for him to deliver the goods. Did he have the goods to deliver? So Mueller's going to show the goods over in Berlin in September. There's a conference, big Fifth International Congress on September 11th through the 18th. And so Mueller has got to get everything ready and put it all together. And he's harassed, he's this, he's that. In fact, in his third experiment, he doesn't even include a control group because he doesn't even have time to do it properly. And he was off to Berlin on a boat, and he's trying to write his presentation while he's on the boat, and whatever it is, he delivers. He shows his data at the Congress, and he leaves Berlin a big scientific star. And it was the wires and everything. They had Mueller as he induced gene mutation, and so forth. Now, it was interesting. The paper that was published in the conference proceedings, and the paper had no methods and materials, It cited no references. It didn't discuss anybody else's work. I've pretty much proven, I think, to myself, and maybe the world who follows my papers, that Muller's Nobel Prize work was definitely not published. And anybody who's interested in following up on that, those historical aspects can see all the details behind it. So Mueller plays a game, and the game was that he beats everybody else by not playing by the rules, gets his paper in Science, the most significant venue. He has his data, kind of proves to people superficially, but he doesn't play by the real rules of putting those papers and those data through a really critical peer review. So he comes back, he's a hero at Texas. He's Mr. Big for a while. And so what happened is he got a couple of graduate students to follow up on his work. And this is where we come into the LNT issue. So Muller's dose response studies in his own Nobel Prize work were not strongly dose response oriented, but he had two students who followed up on his work, working at extremely high doses, and he showed a linear dose response in these two studies. Now, I want to, so what he does at this point is in 1930, Mueller decides, based on these two student studies, that he thinks he knows the nature of the dose response in the low dose zone. And he makes a type of proclamation in the form of a paper. And he writes that the nature of the dose response is a linear dose response for radiation and mutation, all the way down to a single ionization. And he didn't call it a linear dose response, he called it the proportionality rule. And that was the precursor term for linear dose response or linear non-threshold dose response or LNT, whatever we call it today. Mueller actually creates the concept in 1930. And he does it for radiation-induced gene mutation. And so what happens is that at that time, there's he's all on his own, because the pharmacologists have already established that the basic dose response is the threshold dose response. Mueller says you can have your dose response, that's fine, but when it comes to mutation and it comes to radiation, it ain't a threshold, it's a linear dose response. And so this began this conflict between Mueller and the medical community that would continue for, I'm going to say, the next 25 years. And so Mueller was a very doggedly persistent individual who wanted to fight to convince people that he was on the right track and that this dose response to mutation had lots of implications.
And so he was at the time challenging the threshold model. Hormesis did not have a place on the stage, the scientific stage at that point, correct?
Hormesis is buried 6 feet under.
Okay, so basically the main challenge was to the old toxicology saying, which is the dose makes the poison, basically.
That's right. And basically, there was always a safe level. Below a certain dose, it was safe. Mueller said, that ain't the way it works. Mueller says it's a linear dose response. And Mueller was very interested in whether, in the medical implications of this for X-rays for pregnant women, what it would mean for children, things of that nature. And Mueller was putting a lot of pressure on the medical community. And the medical community was coming right out of, it was the medical community and their pharmacologists and others. I mean, this was the medical establishment. Mueller was really anti-medical establishment, very basic science establishment. And he wanted medical practices to change, to recognize the risks of ionizing radiation. And the field really couldn't cope with him at the time. He was more advanced at the time. And so what happened though with Mueller is Mueller got into a lot of conflict with other scientists at the time, because I have to tell you that the dose that Mueller actually induced gene mutation is becomes significant, okay? My calculations, and I believe that they're correct, they're published and been checked over many different ways, that Mueller Mueller actually gave a dose that induced gene mutation that was 95 million times, and I mean million, times greater than background. So we're being exposed to some background radiation here from cosmic rays and from background radiation from the Earth and so forth. And we can tabulate what that is, over the course of, let's say, a year or a day, however you want to do that. But Mueller goes in and he gives 95 million times that dose, okay? And that is it proves to be a whopping dose, okay? A whopping dose, even to relatively insensitive insects like the fruit fly. And
okay, so I think it's worth it to point out that all dose response curves agree on one thing, which is high doses are harmful. So I don't think any of the dose response functions we've discussed so far would disagree that if you are subjecting any living being to this level of radiation, that harm will not be induced, correct?
no, that's absolutely correct. And what we have here is that when you look at the fruit flies that Mueller blasted with his radiation, many of them died. Okay, so he was giving high doses, and those that were lucky ended up being sterile. And most of them did survive, were sterile. Some may not have been, but whatever it was, they were a ragtag group of fruit flies that made it through Muller's experiment. So he was really shooting pretty high when he induced what he called gene mutation. Even the two students who followed up, my calculations are that they were giving anywhere from 30 to 40 million times above background at their low dose. I mean, so just picture this. If the low dose is 40 million times, 30 million times background dose, Muller's extrapolating over how many orders of magnitude of dose to claim that there is a linear relationship all the way down to a single ionization. It's mind-boggling extrapolation in today's world.
And so walk us through now how this LNT model made its way to the regulation of radiation.
Oh, how did it make it through? Well, it's a long struggle for Mueller. Mueller was Mueller was a academic combatant, so to speak, against the establishment. The establishment was the medical community, and Mueller was trying to convince them that this new great technology, which was really X-rays and its application to medicine, you had to be careful. It could cause mutation, and other people began to see mutation, and he began to develop a cadre of followers. And so what happened was that nonetheless, through all this, see, Mueller had argued that he had induced gene mutation, right? But in the fight of scientists afterwards, some smart people, there are people just as smart as Mueller out there who may be even smarter and better in the laboratory than him. And one of them was a guy from the University of Missouri whose name was Louis Statler. And Statler worked with this lady who was another Nobel Prize winner, Barbara McClintock. And she was at Cornell, and then she went out to work with Statler. And she was a corn cytogeneticist. And Statler was a corn radiation geneticist. And Statler was only a month or two or three behind Mueller. And he played by the rules, and he submitted his data, and he published his paper with his data in Science. He actually played by the rules. But Mueller beat him for different reasons. But as it turns out, he gets Barbara to go out to Columbia, Missouri, and to look at what he his corn under a microscope with new staining techniques. And he says, look at my gene radiation-induced gene mutations and so forth. And so she looks at this with new resolution, improved resolution with wonderfully improved staining techniques to look at chromosomes in many different states of presentation, in mitosis or meiosis, contracted, elongated, what have you. And when she did, she says, what you think is what you think is a gene mutation, you're just blowing holes in those chromosomes. You're inducing massive gene deletions. She says, you've confused an observation with a mechanism. She says, yeah, you got what I'd say transgenerational phenotypic changes in your corn, just like Mueller got transgenerational phenotypic changes in his fruit flies. She said, but in your case, for sure, you didn't induce this with gene mutation. You did it with gene deletion. That means it's not very significant. People back in 1922 were able to do that.
And so this scientific process, even, minus the big mishap with the publication of the article in Science without the evidence necessary for the publication, the scientific process was working out more or less properly. Like there was challenge from other scientists to Mueller's findings, but somehow this LNT dose response did end up making it to our regulatory agencies, from the EPA to the NRC to the FDA. How did that come about?
Yeah, and I have to say that over the course of the 1930s, Statler became, he outplayed Mueller in the laboratory and in the interpretation. And Mueller was actually backed, it was like two smart people in a high stakes game of scientific chess. And as it turns out, Statler, in a chess match, if you're a little bit better than the other one, you take 70 moves, you eventually back somebody into a corner and you get their king. Well, after 10 years of laboratory competition, and I've bought all their grant proposals and I have all their papers, and I've watched this chess match between Statler and Mueller, and Statler had him backed up. And so what happened was that Mueller knew this, and Mueller's a smart guy. He's a rival of anybody, actually. He's a very smart man. And he knew that Statler had him around the neck, and he wasn't going to let him go. And so he had to come up with, he's smart enough to know if I keep doing the same play again, I'm not going to win. So he had to come up with a new idea. And his new idea was, well, I'm going to take a look at this issue of what's called dose rate versus total dose. And it's very simple. It's the piggy bank model of a dose response. And this Mueller accepted the piggy bank model. It was that every single exposure is harmful. The damage accumulates. You can't repair it. It's irreparable. And if you then stretch this out like a piggy bank, the dose response looks very linear. And the other thing was that if you have a dose rate model, then you have to have a rate that is so great that it's faster than your repair capacity can handle it. But if it's not so fast, then your repair rate can handle it, and you'll get a threshold. And so what happened is Mueller believed that, in fact, if he could show that it was total dose that could explain this phenomenon, then he could apply it both to the LNT, or this linear dose response, and he could reclaim his position on gene mutation, because you could bring it all the way down to a tiny exposure. And so that's what this fellow did over in the graduate student, tried to save him over in Edinburgh. And so in the graduate student, this becomes very interesting again. It's Mueller. It's Mueller. He's you got to picture the personality of this guy. Let's say that he's the smartest guy in the room, and I wouldn't dispute that at all. And he's creative, and he's a darn hard worker. And I know that from all the papers letters and everything that I've read. He's outworks everybody, this guy. But he's got some weird personality quirks. I mean, the idea that, what kind of a personality is it that knows that all these people are closing in on him to who's going to be first to get this, and he has the audacity to use a personal favor to get the editor of Science to publish his paper without any data. I mean, that really, how do you think the other people must have felt with this, right?
And so how come none of the people challenging his model were capable of influencing our regulatory policy? So I want to dive deep into our regulatory policy. How did the LNT model makes its way to as the default model for any carcinogen, and radiation is considered to be a carcinogen, and also to our regulation of PM 2.5 by the EPA. How did this model become the default model?
It made it because of the Manhattan Project. Mueller comes back from Edinburgh with some support for his dose rate thing, but he gets hired as a consultant to his friend, the guy who helped him with his paper over there in Germany back in 27, and they are trying to support this proportionality rule, LNT. And this was the big key. This was like major stuff. And so back in the Manhattan Project at the University of Rochester, there were two studies, big studies that were done. One was they were really trying to replicate this Edinburgh thing, but in a big way. And they had a big problem. One study showed that it was a linear dose response, but it was an acute study, very high doses. Second study was the chronic study, giving a high dose, but in tiny amounts spread over every single day of the fruit fly's life. That study does not support linearity. It supports a threshold. It becomes this thing called the Kasperi study, and it's the fly in the ointment. Everybody was hoping that these two studies would come together, and bingo, that's the pincer move. We're going to support LNT, and that's what happened. And man, it just caused everything to stop. And so what happened is that despite that, Mueller and geneticists at Rochester, even the guy who did the studies, they were so wedded to Mueller's perspective that they said that in fact, even though they had a threshold, that they didn't want anybody to believe it or accept it, even though they kind of did it okay. We don't know why we got it. It must have been something that was weird with the study. And they wrote that up, and that's what they published. And Mueller goes to his Nobel Prize speech, and this is where it begins to turn. You got a picture.
What date was that?
On December 12th, 1946, over in Stockholm. Mueller stands up in front of the Nobel Prize audience, and Mueller tells the Nobel Prize audience that we can no longer adhere to a threshold dose response. We have to shift over to.
We lost Ed.
What's that? You lost me?
I think we lost Dima. Let me try to get her back on.
I think we're back.
You're mute.
I think we're back. Ed, sorry, we were talking about the Nobel lecture that was in 1946, correct?
Yeah, and Mueller makes this audacious claim that you can no longer have any trust in a threshold model. You have to go to a linear model. Now, right before, like 3 weeks before that, Mueller has seen this biggest, best study ever by this guy Kasperi that supports the threshold model, and he acknowledges that it's a strong study. Acknowledged in writing it needs to be replicated. I could not find any flaws with it. Yet Mueller goes in front of the world community at the Nobel Prize, and he essentially, in my opinion, he deceives the audience. He misrepresents what he understands, and he's trying to lead them down a particular path that he's tried to push ever since 1930. And here's his moment. And only he and a couple of people at Rochester know that the biggest, best study to date is a threshold study. And I have to think back to the nature of the character of this man, this outstanding man, the smartest guy in the room, man. He's doing another science journal again. He's rolling the dice and doing, taking this high risk sort of an operation. And so what happened is that in fact they had to go and they had to try to replicate this work. And so 3 experiments were done
And
back
let
at
me just
Rochester.
stop you right here. So basically, we're talking about 1946. So he wanted to push the LNT narrative for a very long time, but wouldn't you say that now there was a demand for the LNT narrative when it comes to radiation, given the fear of nuclear testing and also the nuclear bomb at this time?
Well, he may well have got the Nobel Prize because of the response to the atomic bomb 1 year before, because it got such prominence, and he was taking advantage of all of that, actually. And what happened was that some strange things happened, because Mueller is a scientist. He's still a great scientist. He wanted that. He probably believed that the LNT was right anyways. Maybe he even believed that, even though the data didn't support it. So 3 experiments were done back in Rochester with follow-up money to try to discredit this threshold result. And I'd have to tell you that the bottom line is, without getting into the minutiae details of these 3 studies, the bottom line of these 3 studies is none of them have been peer-reviewed. None. Okay. The data of 2 of them, I have no idea where it is. I don't think it's ever made it out into the scientific community. One study that was given to the funding agency, which was the Atomic Energy Commission. The 2 authors said that the data were uninterpretable and may have been the product of scientific bias. These 3 little experiments, they were summarized in Science, in the journal of Science, summarized in a note by the head person up there at Rochester, to discredit the threshold model study and to promote this work that had significant questionable problems with it. And they claimed that they were going to provide all the data in a subsequent paper, which they never did. But the key issue here is that the radiation geneticist community, and ultimately later National Academy of Sciences committees, they cite this 1-page scientific table, article, and this becomes the most important paper in the establishment of LNT, and it's based upon data, again, that were not peer-reviewed, worse than Muller's Nobel Prize. 2/3 of the stuff you can't find anywhere, and the one paper that you can find, they claim that it was not interpretable. And this is what the basis of LNT historically is, because what happens next in this crazy story is that there's a very famous professor from MIT. His name is Robley Evans. He's a radiation physicist. Without going into all the stuff he did, but he wrote a paper in Science in 1948 in which he saw this threshold study from Rochester that supported that didn't support LNT. It supported a threshold, and he's a big name. And Mueller got really upset with this and tried to rally his troops to try to thwart this. And I believe that what that led to was Mueller had 2 or 3 or 4 studies published from 1950 to 1954 in which he absolutely lies in the literature. He contradicts his own data, other people's data, contradicts all the communications between him and the people at Rochester, which I've pretty much documented in spades and in different articles, to hold his team together. And he's getting very brazen, maybe even brazen after he wins his Nobel Prize to do that. But what happens is that as a result of all the controversies in the Cold War and between the US and the Soviet Union, the Rockefeller Foundation convinces the National Academy and President Eisenhower to have the National Academy create a bunch of committees that could advise the country on what to do with all things nuclear. And for the very first time, a genetics committee is created, and it's created to guide the government. And it's this committee that institutionalizes LNT within our country and the rest of the world, and it becomes adopted by the US EPA.
So is there evidence that the Rockefeller Foundation has sensed back in those times that nuclear can become the next big source of energy, and obviously would be a great challenge to oil, and therefore they had an interest in pushing the narrative of LNT when it comes to radiation?
You know, some of my people that I know pretty well have taken that position, and they've looked at maybe Rockefeller as an entity much more deeply than I haven't come to that conclusion. I haven't really resolved it. I mean, on the surface, that could be, but whatever it was, Rockefeller was powerful. They had a lot of political clout, and they were able to write directly to President Eisenhower and tell him that they think that they should, you know, concerns with genetic damage. We will pay for, you know, a study. It could be done by the National Academy, but what they didn't tell Eisenhower in this letter, I don't think, not that I can remember it, that actually the president of the Rockefeller Institute for Medicine was actually the same person who was president of the National Academy of Sciences, and he was also on the Rockefeller Board of Directors. Detlef Frank. They had the ultimate insider in terms of powerful influence. But the big key is, you know, when you put together a committee, it's like putting together a jury. It's you fight over who's going to be on the Supreme Court. You fight over who's going to be in a jury. You fight over who's going to make the decisions, right? And I can tell you, the person who was put in charge of the genetics committee was the research director of the Rockefeller Foundation. It was not a geneticist. The person who funded all these academic geneticists through the Rockefeller Foundation. They knew the position of all of them with respect to LNT and mutation. And the jury was stacked. And they stacked it with people who they made their Pledge of Allegiance, their Apostles' Creed to LNT. And it's all in the transcripts of this committee back in 1956 when it was working.
And the AEC, which is the Atomic Energy Commission, later on was dismantled and its duties were given to the EPA, the DOE, and the NRC. So the NRC is in charge of regulating nuclear energy, and EPA, among other things, but they regulate health regulating health exposure to radiation like X-rays, and then we have the Department of Energy. And am I correct to say that the NRC still up until this day adopts the linear non-threshold in its regulation of nuclear energy, and the EPA as well in many things, including particulate matter 2.5, even though that is not considered a carcinogen? They belong to the LNT club. They're the LNTers, and really where it came from was it really came from this Baer Committee back in 1956, and the Baer Committee did a big thing. It basically emasculated the AEC, and it emasculated it politically in the eyes of Eisenhower. And they were a powerful group, but one of Eisenhower's last big acts in 1959 was to remove all the authority from the AEC for all health risk evaluation, and they created a new entity called the Federal Radiation Council, 1959. And this is really weird. Am I looking at the history of who advised them and who didn't in their committees? They then took the LNT biased committee of that 1956, and they became essentially members of their advisory committee throughout the the 1960s. And so Mueller, it was like the perfect takeover in terms of getting your ideas established. The agency that was opposing you gets emasculated. The president creates an alternative and stocks it with people who are LNTers. And then what happened is that when Nixon created the EPA, he just defunct, did away with the Federal Radiation Council, took all those people and put them into EPA and seated them with LNTers. And so all they really did when it came time for EPA to flex its muscle and decide how to guide the country on carcinogen risk assessment, they just looked into their 1956 playbook and they said, we're going with LNT. And then because half the problem they were dealing with were chemicals,
They had to come up with a strategy for chemicals as well. And they said, well, since radiation acts through a mutation and chemicals do as well, we'll just assume that the chemicals act via an LNT as well. And that was actually stated in their regulation back in 1975. And that's when they first came up with it. And really, as the twig is bent, so grows the tree. And that's really, if one wanted to consolidate it, that's the long reach of Mueller. The long
And
reach of
so,
Mueller.
in your opinion, I want to leave the last 15 minutes for questions. So I ask our audience to please put their questions in the Q&A. And of course, you can raise your hands and I can have you come out and say your question. But my final question to you, Ed, in terms of our regulation, the obstacles that we have in front of nuclear energy, what portion of it comes back to the LNT assumption, the linear non-threshold assumption, the fact that one molecule exposure is going to create proportional and irreversible harm?
Well, it really breaks down to not understanding science, not understanding evolution. To me, the big problem, surprising problem with Mueller was he's an evolutionist. I mean, he's a geneticist. The big thing with me in trying to understand what's the nature of the dose response in the low dose zone, and that is we're all survivors here on Earth, survived a massive, long evolutionary process. Well, survivors actually have the potential and the traits to resist challenge, stress, harm, to repair damage, and Mueller's perspective that he created back in the day was this piggy bank model that all damage was what? That all damage was cumulative. There wasn't repairable. It was irreversible. And what we have learned really since the late 1950s is that that's not the way it works. And that is that at low dose, what goes on at low doses can't be predicted from high very well at all. And that there are a plethora of adaptive mechanisms that allow you to repair all sorts of damage and to overcompensate for damage and in fact even decrease background damage when you have these adaptive mechanisms there. So I think that what's happening here in terms of our regulatory framework is that they're so decoupled from an evolutionary understanding of life. They base their understandings and models on epidemiologic studies that are insensitive and that can't actually have very good discernment at very low levels. And what really is to be understood is underlying mechanisms and really adaptive mechanisms to see how all creatures, all cells adapt to low-level stresses. It would really change radically our understanding of really the truism, as I see it, is that we're not victims. We actually fight back. Whenever we are challenged, damaged, stressed at the cellular or other levels, we, if we're going to survive and win, then we actually have to have the capacity to repair damage. And until the groups like the EPA understand better and integrate better evolutionary understandings into regulation, we're going to be seeing ourselves within the framework of lower is always better. Any damage is always bad. You can't repair the damage, and it just sees us as environmental victimhood, and it's not really the way evolution works.
With these words of wisdom, I am going to open up the floor for Q&A. I have a couple in the chat, but please feel free to raise your hand and I can bring you to ask your question live. I'm going to take one question from Bill Kleinbecker in the chat. Can this homeopathic phenomenon be traced through the archaeologist's finding about things like ages, geophysical events, and species migration?
Well, I don't. The homeopathic is I don't think relates to geological or migratory activities. It's a medical treatment philosophy and scheme, and it was really created to try to come up with an alternative for what I would call would be really terrible heroic medicine practices in the early mid 1900s, 1800s, and essentially where people were treating patients with toxic chemicals or leeches or other types of modalities, and so I'm not sure that I can really do better than that on my answer.
And with another question, did Mueller meet up with Einstein to make waves about the danger of extreme radiation? Some with Oppenheimer and Mueller. Same with Oppenheimer and Mueller.
I've looked into the people that Mueller has interacted with, and I have not found his interactions with Oppenheimer or with Einstein. And I actually looked into them with Linus Pauling as well, and there may have been a letter or two between him and Pauling, but who was a very powerful leader in the 1950s for essentially the LNT, as well as test ban treaty, things of that nature. But I didn't see Mueller in that particular area.
So Ed, what advice do you leave us with? I know that the NRC has been challenged. Years back, there was a petition to the Nuclear Regulatory Commission to let go of the LNT hypothesis and adopt more scientifically supportable default models, particularly the hormetic model, and if not the hormetic model, the threshold model at a minimum. And that petition was just recently, I believe in just 2020 or 2021, rejected by the NRC. So in what ways can we take the lessons from evolution, from biology, from science, from the story of corruption that you're talking about and the political influence? How can people combat that to change our default model to something that is more scientifically sound?
Well, I actually think that it's really the answer is in challenging people to understand their history. We've only really scratched the surface of the corruption, and it's serious what we've scratched. But there's much more to the story. And what I would have to say is that regulatory agencies such as EPA have never made the effort to understand their history, ever. They've been in business for 51 years, and it takes somebody like me, not a professional historian, to go in and dig out all the skeletons and to lay them up and stack them right in front of their eyes. It should be embarrassing to them. And yet they don't respond to it. And so I don't have a lot of confidence in the agency as one that is a searcher for truth. They're a searcher for maintaining the status quo and to probably preserve their job and their power, but they're not a searcher for truth. And so I think they have to be forced to somehow really look into the history of how their regulations came to be, what they were based on, because as I said, as the twig is bent, so grows the tree. When the decisions were made, they've stayed with those decisions, and those decisions are based on corrupt science and misleading advice and every other form of dishonesty that you can imagine. And so I think this is our history, and the American public really needs to know its history, and they have to force our regulatory agencies to basically become honest with themselves and with the public for the first time in their life, maybe. They're afraid actually to look into the historical mirror, afraid what they might find.
And we're going to have another webinar in the spring to talk particularly about the health implication of hormesis. I know that you've had some research into the use of radiation and even treating the bad cases of pneumonia as a result of COVID with very promising results. But unfortunately, we have the LNT hypothesis that's standing in the way of adoption of a lot of these medical treatments. Today's session was trying to focus on the evolution of LNT and how it made its way to the Nuclear Regulatory Commission, and it's still the default model as of today. Though I do wonder how we are going to maintain our hatred for fossil fuels, but at the same time, our love for LNT. Because our love for LNT is preventing a very safe and effective energy source, nuclear, from being adopted. And our hatred for fossil fuels speaks for itself. It needs an alternative. But with LNT, we can't have that alternative. In the spring, we'll take a dive into the health implications. But Ed, thank you very much. This has been an absolute pleasure. Your story is always mind-blowing every time I hear it.
Thank you very much, Dima.